Again, to reiterate the steps for a bootstrap, we generate this E star, so we're sampling with replacement from the residuals. Then we calculate that Y star, so that's basically using those resampled residuals and adding them to our Y hat to get this new Y star. And then we compute this beta hat star, this test statistic that we're interested in, this beta hat from our X and Y star. And so I've done this. I've gone from 1 to B. I've done 1,000 of these. I end up with 1,000 different boot coefficients. And we can plot those. And so here I've used ggplot to plot that data frame boot underscore coefs. And my x-axis is horsepower because that is the name of the variable that shows the beta coefficient associated with horsepower. And I plotted a little histogram. And so this is what we get for that distribution of that beta coefficient. And so now if we wanted to try to estimate some uncertainty, we could do something like, for example, maybe we could decide that we'll cut off basically, if this is, we're assuming this is like the underlying distribution for beta hat, and so we can sort of cut off the 2.5% tails on either side to try to construct something like a 95% confidence interval. So let's talk about how to actually do that. So in R, you can use the quantile function, and this is going to get you what's known as a percentile confidence interval. And so what I'm doing is the quantile function is a way to calculate sample quantiles. And so here I'm going to calculate the 2.5th percentile and the 97.5 percentile of the horsepower bootstrapped coefficients. And so this is going to be my lower bound, negative 0.17. And this is going to be my upper bound of my 95% percentile confidence interval, negative 0.1449. So the bootstrap percentile confidence interval for the coefficient for horsepower is negative 0.170 to negative 0.145. We could compare that to a confidence interval calculated using the traditional method that we learned last class. And so in that, if we were just using the conf_int function on that linear model using just our observed data, we end up with a confidence interval from negative 0.175 or 1705, so a little bit slightly different than this 170, and negative 0.1451, so pretty close to this. There's another method for calculating a confidence interval using the bootstrap, and that uses the standard error. And so we can also calculate the average coefficient and the standard error for these bootstrapped coefficients. And so the average beta coefficient would just be taking the mean of those coefficients that we get for horsepower. And the standard error would be just taking the standard deviation of those coefficients. And so the standard error method is going to calculate a slightly different bootstrap confidence interval. To do that, we're going to use the normal, what we're used to as a definition for a confidence interval. But instead of this beta hat, here we're going to plug in that average value that we got from beta star. And the standard error, we're going to plug in that standard error that we calculated from the beta star values. And then we're going to multiply that by a t-star, which is going to be the same t-star that we would use normally under normal conditions, which in this case is going to just be from a t distribution. And so we end up with negative 0.17 for our lower bound. Again, quite close to what we get in the percentile case and also in the traditional method. And then we end up with negative 0.145 for the upper bound, which again is quite close. So let me just draw all of those together so you can sort of see how they all compare. And so here I've drawn the percentile bootstrap, so that's the solid line here. This is the percentile bootstrap over our distribution of potential coefficients from our bootstrapped model. These dashed lines here, this is the standard error method. So this is the bootstrapped standard error method, and as you notice, it's a little bit different than the solid line, but pretty close. It looks like it's a little bit more conservative, meaning that it's a slightly wider confidence interval. And then this dotted line here represents the confidence interval that we would get if we calculated it via the traditional method. And so all of them tend to be pretty close. Okay, so what I want you to do is I want you to calculate a Bootstrap percentile confidence interval for the coefficient associated with weight from that model that you fit in the previous exercise. And then I want you to calculate a Bootstrap confidence interval using the standard error method for the coefficient associated with weight. And then finally, I want you to compare these intervals to the interval computed using the confint function. So go ahead and work on that, and when you finish, knit your file and submit it to Canvas.